Fast suggestions are not automatically useful. Keystroke savings and MRR reveal whether autocomplete reduces typing and puts the intended query where a user will actually choose it. You'll learn how the pieces fit into a workflow that scores typing saved and ranks the first correct autocomplete suggestion. I'm Professor Pi, teaching search and IR with simple Python. Autocomplete feels easy until you try to measure whether it actually helps people. Teams ship suggestion models and then wonder why clicks don't budge. The gap is subtle. Users decide at every keystroke. If you only look at the final ranking, you miss the early decision points where a user might already have chosen something. This evaluation treats autocomplete as many tiny decisions in a row. Two metrics matter. 1. How many characters does a suggestion save the user from typing? 2. When the intended query shows up, how high is it in the visible list? Together, those answers tell you if suggestions genuinely reduce effort. We'll build a tiny offline test, turn queries into prefixes, simulate what's visible, and report both keystroke savings and a rank-aware score. The code stays lexical and small, so the logic is obvious before you swap in a learned ranker. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need to turn a target query into the prefixes a user actually types. This snippet turns one intended query into the prefixes a user actually types. Autocomplete evaluation starts before ranking because the same final query creates many decision points after 1 character, 2 characters, and so on. The prefixes list makes those decision points explicit, while truth marks the query the user is trying to reach. The toy queries list is deliberately small, so the prefix behavior is easy to inspect on screen. The visible output confirms the early prefixes and the final pre-completion prefix, which anchors the rest of the evaluation. Now we must decide what a visible suggestion means for typing saved. Next, we measure whether the interface saves typing, not just whether it eventually knows the answer. This example measures whether the interface saves typing, not just whether it eventually knows the answer. The Suggestions Dictionary maps prefixes to the visible top suggestion, and hit at finds the first prefix where truth is ranked first. Keystroke savings is computed as the fraction of characters the user no longer needs to type after selecting the suggestion. A system can feel responsive at C or CO, but if the intended query is missing or displaced, those early states do not save work. The output shows the first selectable prefix and the resulting typing avoided. Finding the first selectable prefix is useful, but it hides where the intended query sits inside the suggestion list when it appears. Then we add a rank-aware score, so presence in lower positions gets partial credit. This code scores the rank position of the intended query at each prefix. Keystroke savings only asks when selection becomes possible, but MRR adds pressure on where the correct suggestion appears in the list. The helper RR returns 1 for rank 1, 1/2 for rank 2, and 0 when truth is absent. Averaging over ranked gives a prefix-level MRR, which is often more diagnostic than a single final query ranking score. The output shows that the intended query is present early, but not always in the most selectable position. But interfaces rarely expose long lists. If users only see the top row, lower ranks may be worthless. Now we consider what the user actually sees by limiting the visible list. This snippet checks how much evaluation changes when the interface only exposes the first suggestion. If users usually pick from a narrow visible list, rank 2 may be much less valuable than it looks in an offline candidate set. The top K cutoff truncates each prefix list before calling RR. Then the code compares that stricter view with a top 2 view. Increasing top K can raise the score when useful suggestions sit lower. But it may overstate usability if the UI rarely gets attention beyond the first row. The output makes the cost of a shallow display visible. We still need a compact example that ties save typing, rank, and a simple popularity baseline together. Finally, we tie typing and rank together over a small query log and a simple suggestion baseline. This example pulls the pieces into a compact offline baseline. The FREC table stands in for query log popularity, and suggest returns prefix matches ordered by frequency with a deterministic tiebreak for each query in tests. First OK finds the earliest prefix where the intended query is visible in the top 2. Then the code computes both saved typing and reciprocal rank at that selection point. This is a simple lexical baseline, so a neural or learned ranker would replace suggest in a real IR experiment. The output reports the two metrics together, showing both effort reduction and rank quality. Mapping this toy to a real system is straightforward. Replace freq with your product query log. Run suggest with the candidate generator you plan to use. And report keystroke savings and MRR on a held-out set of real queries. That combination gives product teams numbers they can act on. We measure two things together: characters saved and how visible the correct suggestion is. Use this when you need to know whether suggestions actually reduce typing and are likely to be picked. One caveat: presence deep in a long candidate list can overstate user benefit if your UI only shows 1 or 2 options. Try different top K cutoffs on your query log. Rerun the same small test with top K set to the UI width you care about. That one experiment often points to the biggest product win. If short, practical IR helps, subscribe and watch the IR videos.